sir. Thank you so much for joining, Radhika. And
Hi
so,
Radhika, your volume is a bit low. I don't know if it's on my end, but I can barely hear you.
Radhika madam, you are not audible.
sorry, am I?
Very faintly.
Just okay. Now is it better
Yeah, a bit better.
or not much?
A bit better from.
Yeah, ma'am. Can you hear me?
Yep.
Tina, madam, you were trying to
Yes,
speak
madam.
up something? Okay.
Yes,
All good?
yes, madam. Yes, madam.
Yes,
Now you are audible.
okay, fine. So, sir, it's 11. With your permission, can we start?
Yes, please. Yes, go ahead.
Okay. Dear participants and our respected keynote speaker for today, Mr. Vikas Ramachandra, sir, my fellow co-coordinators of the STP, my superiors who are not present here, but we duly acknowledge them. And on behalf of KJ Somaya Institute of Engineering and Information Technology, Sion, Mumbai, I welcome you all for the keynote talk of the short-term training program on leveraging artificial intelligence and data analytics for healthcare, sponsored by All India Council of Technical Education and organized by Department of Information Technology for the next 6 days, that is from January 4 to 9. This is Dr. Radhika, the head of Department of Information Technology and coordinator of the STTP. The COVID-19 pandemic has impacted almost every sector and geography during the previous year. In difficult times like this, KJSIIIT has taken an initiative to contribute towards the healthcare sector through cutting-edge technologies, AI, and data analytics. In fact, healthcare and agricultural research have been the focal points of Department of Information Technology. As a support in our mission of contributing towards healthcare sector, we have been sponsored by AICTE and we'll be using this opportunity provided by AICTE under the Quality Improvement Scheme 2019-20 for the better upliftment of all the research scholars and faculty members who have been a part of this STTP for 6 days. We aim to apply data analytics and AI for sustainability, resilience, and enhancement in healthcare. And there can be no better keynote speaker for us than Dr. Vikas sir. It was a great gesture from him to accept our invitation and deliver the keynote talk. It is late night for him, I understand, and still he's spending time for us. We have him for 1 hour, so I'm glad. And to introduce the speaker, Dr. Ramachandra sir is expert in healthcare analytics, machine learning and computer. With a Google Scholar citation in 4 digits, more than 2634, index 29 and H index 19, sir is a doctorate from University of California, San Diego. He is a faculty at Columbia University, New York. He is also the co-founder and CTO of Onward Assist, Hyderabad. Sir is an adjunct faculty at Fordham Gabelli School of Business, New York. He is a voluntary data scientist and machine learning consultant at UNICEF, voluntary instructor at Room to Read, California, voluntary instructor, University of the People, California. Sir has worked for 15 years in the industry, and in fact more than 15 years, if I'm not wrong, for Fortune 500 companies on several machine learning and computer vision R&D products and projects. He's worked for consultancies over a dozen of startups in the analytics space. Sir was a former adjunct professor at UC Berkeley. He was also the former data science consultant at World Bank, Washington, D.C. He was the senior data scientist at Roche, Switzerland, staff research engineer at Qualcomm, California, the lead data scientist at CureMetrics, California, staff data scientist at Stanford University, California, the director of data science at Bright Inside, California. Sir has been granted 15 patents at such a small age, and he has authored hundreds of papers in journals and conferences of international repute. Sir is the instructor, curriculum designer, and mentor at various campuses and universities. And we cannot be more fortunate than this to have him to kickstart the STTP with his keynote talk. I'm glad, sir, that you accepted the invitation, and I was more than excited to convey to my fellow colleagues that we have such an eminent expert who will be taking us towards the entire 6-day journey by giving a great beginning. So we thank you so much for joining and accepting our invitation, and it will be all a great learning experience listening to you. Since there is a very limited time, I'll not take long, and I thank the principal of the institute, Dr. Suresh Ukrande sir, and the vice principal of the institute, Dr. Sunita ma'am, for giving us this opportunity to bring you on the platform and connect to several experts and the participants from almost 18 states in the nation. And being a virtual conference, we have been fortunate to connect all of them together. So thank you so much, and over to you, sir.
Yeah, thank you, Radhika, for the very warm introduction. I think it sounded better than I really am, but yeah, it was nice to hear. Let me start by sharing.
Okay, sir, we can see your screen now.
Yeah, it's visible. Yeah.
So you are on mute.
Yeah, sorry about that. Sorry for the delay. So I think the topics I worked on mainly, I think I'll quickly get into it. I'll skip through some initial slides I had in terms of my introduction and so on, since Radhika already gave a pretty good introduction. So a couple of directions I worked on. It's been mainly in the healthcare domain. It's been a lot of medical imaging, machine learning for medical imaging work, which is what we focus on at Onward Health. I'll come to that in the very end. I'll talk a couple of minutes about that. This talk, however, I'll be focusing on something known as causal inference and how we can use machine learning, and I'll talk about how this is actually useful in the healthcare domain and how this is actually something which can solve a bunch of healthcare problems with a general framework. And I'll get into more details as we go along. Yeah, let me skip through these background slides. Okay. So yeah, you must have heard a lot of talk around
So sorry to
causality.
interrupt you, sir. Can you please get it in a slideshow mode?
Sure.
Yes, sir. Thank you so much.
Can you see it? Okay, so yeah, so I think a lot of the stuff which we see in machine learning, and I'm sure many of you have a background in AI or ML, is pretty much what we call as functional estimation, right? So you have essentially you have your y's, which are essentially your output variables or dependent variables. You have a bunch of covariates or features which are known as x, and what you're trying to learn essentially is this form of y equal to f of x, right? You want to learn that function f, which relates y to x. However, in the real world, what we're really interested in beyond that is what causes what, right? So what we want to learn is, does a particular action cause a change in a particular output, right? So and then this goes beyond traditional machine learning. Because in machine learning, what essentially we're trying to do is learn that function f of x, which learns the correlation between your dependent variables y or the output and your input or the covariates, which are x's. So basically, what's the difference between causality and correlation here? So in causality, what we essentially have is an additional input or an additional variable, which is known as treatment, right? So essentially, you take an action or you cause an intervention, right? And then in the healthcare domain, it can be pretty useful to learn this because, again, I'll get into that in a little more detail. But then you're very interested in knowing what is the effect of giving a medicine to a particular patient, right? As opposed to giving another type of medicine. You're interested in the causal change in the patient's outcome or in the patient's health when you actually have a certain type of intervention or when you actually do something. You want to see what change it causes. And so the whole idea is, can we actually use estimation techniques and we use machine learning and so on along with this causal inference framework? This is what I'm going to be mostly concentrating upon for most of my talk today. And this is where I think basically I'll introduce some notation here. So we'll look at randomized trials versus observational studies. So typically when you want to do causal inference, what people do is basically they run a randomized control trial. And in this, basically, what you do is you have a bunch of people or you have a bunch of data points in the population. You can segment them based off of treatment A or B. So you can select a random subset from that group and you can give them a particular drug, for example, and you can give another drug to another group of people. So let's say we call it treatment A or B, right? And then you would see the outcomes for this subgroup who have been given treatment A versus a subgroup who have been given treatment B, and you see the difference in the outcomes. Typically, one of them could be a control group, one of them could be a treatment group for whom a drug was given, and then you are essentially interested in the outcome between the two. This actually tells you what is the causal effect of giving a drug versus not doing anything, or giving drug A versus drug B, and so on. Right? And basically, this is what is mainly done for clinical trials. However, some of the issues with clinical trials is that pretty much recruiting is hard, and the data sample or the data size is pretty small because you have to enroll patients, you have to follow them for multiple years sometimes, and patients may drop out. And many times it's just hard to enroll patients for a particular clinical trial, mainly because, for example, if you take cancer, cancer is a rare disease. So finding somebody who has a particular type of cancer is pretty difficult because it's pretty rare by definition. So you may have to wait a long time, or you may have to run the trial with fewer patients, which actually would mean that your statistical analytical power is pretty low because you have very few people, actually very few data points in your data set. On the other hand, we actually have a lot of healthcare data which has been collected over the years. It hasn't been collected for a particular drug or for particular medicines, but in general, data has been collected for medical records for multiple people, for the data coming from their lab tests, from the pathology reports, radiology reports, and basically all the vital stats, etc., which are collected. And this has been collected for multiple years and stored across multiple countries. So the idea is, or the question here is, can we use all the data which has been collected so far, which are pretty much observational, right? Nobody ran a randomized controlled trial there. It was just collected over multiple years. Can we use that observational data, and can we essentially mimic these randomized controlled trials? And this is where what I'll be talking about, the techniques, would be useful for. So we have a lot of observational data. Can we essentially create a causal inference model using that, which can essentially tell you, what does this tell you, right? So for new patients coming in, it will tell you whether a particular drug is better or the other drug is better in terms of outcomes. And I'll talk about some concrete examples down the line in terms of cancer as well as in terms of heart disease and so on. But then that's the idea. So we have, again, to recap, we have a lot of data which we are sitting on over the years in healthcare and elsewhere as well. We haven't run randomized controlled trials or clinical trials on that data. It's just data which has been collected. Can we somehow look at the retrospective data and mimic clinical trials, or essentially mimic randomized controlled trials? Right. I'll start off with an example which is actually not in healthcare, and this is mainly to set some definitions and so that you can understand what I'm going through in a little more detail. So you have some variables here which we need to understand. So T is the treatment, Y is the outcome, and X's are the covariates. So T, treatment, essentially means a particular drug, for example, in healthcare, or it could be a particular procedure or an operation. Y is the outcome, which could be how well the patient recovers, how long he lives after an operation, and things like that in the healthcare space. And X's are features, right? And for those of you who have experience in AI or machine learning, you know what features are. These could be things like data collected for the patients in terms of their age, their demographics. It could be the patient historical data. It could be labs, vitals, and so on. So it could be all the independent variables which are collected for patients. And again, to make this concrete, the question we ask is, does the treatment T cause a particular outcome Y? And then we are also interested in knowing what's known as counterfactual. So if the treatment had not occurred, what would have happened then, right? Let's say I have a patient P who comes in, and then I want to treat him with a particular drug for heart disease. Let's say I want to do heart surgery on that patient. Now I'm also interested in knowing what will happen to him if I don't do the heart surgery, because essentially you want to see the difference in the two and say actually doing the surgery is useful for the patient. I don't know how much is it useful as opposed to doing nothing, or as opposed to giving him aspirin or another type of drug, for example. This is below an example from the non-healthcare space. Let's say we have a person, Kim, who receives job training, right? And you actually observe that her income after 1 year of job training. So job training itself is the variable T, and then the income after 1 year is the outcome, which is Y. let's say it's $20,000 after 1 year. Now the question is, which you would ask or Kim would ask, is that is the job training really helpful? Did she actually gain from the job training? Right, because somebody needs to spend time and effort, etc., and money on training. So what would have happened if Kim had not taken the job training? What would her income have been in that case? Right, that's the question we need to ask here, because then you can see the difference in the two incomes or the two outcomes in this case, and actually say that job training has helped. Now let's say we had some oracle who would tell us that Kim's income would have been $18,000 if she had not taken the job training. Right? We don't know this, but let's say somebody told us this. Then we would know that the job training actually caused an increase of $2,000 in Kim's income. However, the interesting question here, or the interesting issue here is, you never know what might have been, right? You don't know what would have happened to Kim without the training because you already trained her. So you don't see that what's known as the counterfactuals. So this is exactly the problem of counterfactuals, where you essentially follow one path. You train this person and you saw her income. So you don't know what happens if she wasn't trained. But that's exactly the data point you need, right? And this is another, again, a toy example from healthcare again, which gives you this notion of counterfactual. So you have here age and gender and treatment, right? So you have 40 for the first row. If you look at the first row in the observed set, you have somebody who's age 40, she's female, and then she was treated with particular medication, let's say medication A, and then the BP of that person after the medication was 140. Similarly, second row you have XYZ, some other person of a different gender, age, and they were treated. In the third row, you have another person, 65 years old, female, who was not treated, and her BP is 170, and so on. You have multiple patients who were either treated or not treated. Now, what you want to learn is this is interesting. Right? So we look at the first row here. It's the same person. You have the same person, age 40. She's female. What would her BP have been if she was not treated? And similarly, you can see that if you compare the two rows from the left table to the right table, all you see is the treatment is flipping here. And then and the question marks are the data or the output values you're interested in knowing, you are interested in estimating. You don't know those, right? And I can plot this very simply. Again, this is a toy example. If I plot this, so you have the blood pressure, which is y, and then you have y1 of x and y0 of x. What's 1 and 0? So 1 is basically medication A, 0 is medication B. And then basically for every individual, you have this vertical line. And this vertical line, if you see the blue and the green, I'm sorry, the blue and the red, the difference in this is the outcome difference. In this case, the difference in the blood pressure values when they were treated with drug A versus B. And in the ideal case, you would have all these data points. So you could actually estimate these differences by essentially connecting these via these lines or taking the differences. And I've just plotted this by age. You can have multiple features and it becomes a multidimensional problem. Let me go ahead. And then what you actually have is you have some people who were treated, some people who were in control, which could be medication A versus B. And this is really what you actually have. So for every patient, you see now the dots have changed, right? Some of the dots are solid, some of them are hollow. So the hollow ones are actually the missing data, or what we call as counterfactual. And the solid dots are the ones for which we have the data. And remember, it's for the same patient, right? So for example, for the leftmost one here, you have where my mouse is, you have the blue solid dot, and then you have the red hollow dot. What does that mean? It means that you don't know what the red value is for that person. Similarly, for some other people, you know the red solid dots, or you know the treated values, you don't know the control values. So what you can see is for every data point here, you either know the y1 or the y0, you don't know both. And it's not just you don't know both, but the problem is you can't know both because you cannot do two things to a person at any given time, right? You can either give him drug A, you can give him nothing, or you can give him drug B, and so on. So we only ever observe one of the two outcomes. And this is the fundamental problem essentially with causal inference. And I'd like to actually compare and contrast this with missing data in machine learning, right? So this is not a type of problem which can be solved by throwing in more data. So it's not a big data versus small data type problem. Essentially, this is a fundamental problem in the sense we would need to estimate these values, the missing values here, which I showed, which are basically either the hollow red dots or the hollow blue dots. We would need to estimate this. We would never be able to get the actual values because these are counterfactuals. These are what could have happened if you hadn't done what you did. So you can only estimate those. And it becomes interesting because that's what you're trying to estimate, because what you want to do is for each individual you want this difference. So you have to estimate these missing data points. And also at an average level, right, which is the average treatment effect here. You are interested in that. Going beyond that, actually in healthcare, what you're more interested in is also interesting subgroups of people. So you have these outcome differences at individual level. You have outcome differences at the population level. Now, what you're interested in are there subgroups in the population for whom a particular drug might be more effective, or a particular line of treatment might be more effective? Are there other subgroups for whom another treatment might be more effective? These are typical questions you are interested in a healthcare analytics domain. And for this, again, you'll have to deal with this problem. Again, I think I spoke about some of this. Let me see if I missed out on anything. I spoke about different data points, which are units. Again, just to recap, so treatment is interventions here. We look at a simple binary intervention type situation here where it's drug A versus drug B, or drug 1 versus control who are not given anything. And factual is actually what you see. Counterfactual is basically what you want to estimate, because you want to estimate the difference. That you're not really just interested in the counterfactual, but the difference in the factual versus counterfactual. This actually brings us to the actual framework which has been designed for this. And this is called, going back to causality, there are essentially, sorry, is there a question? I heard somebody ask something. Did someone have a question? Okay, I'll move ahead. I don't think that was a question. Okay, so essentially there are two main frameworks in causal inference. And this typically has been developed by people in econometrics and statistical modeling. And very recently, it is being used in healthcare in the last few years. And I think what's being used more and more now is what people are trying to do in research is combine machine learning methods with more traditional statistical and econometrics type approaches to causal inference. So the two main approaches, one is the Pearl approach, which I'm not going to get into today. And the other one is what's known as the Rubin-Neyman causal model. So again, I'll go through some of these definitions. So you have y0 of xi, and then you have y1 of xi. And this is again the treated and the controlled outcomes, right? Given treatment 0 or treatment 1. And the individual treatment effect here is y1 given xi minus y0 given xi for each individual I. So I is each data point or each patient in the case of healthcare. And the individual treatment effect would be the difference in these expectations. Right, and the average treatment effect is basically expectation of y1 minus y0. So for every individual, you have these individual treatment effects, and then you average across the population. And we are also interested in, like I said, in interesting subgroups or subclusters as well, and we would like to estimate the treatment effects for them. And to make this more mathematical, essentially what you have here is you have the observed factual outcome, which is y of I. And then you have the unobserved counterfactual, which is yi of which is CF. CF is counterfactual, and then you have yi. So these are indicator variables, right? So you have the treatment ti, y1 of xi, plus 1 minus ti, y0 of xi. So basically, if you have treatment 1, you observe y1. If you have treatment, basically you don't observe the y0, right? And treatment 0, basically you observe y0. This is just the way of writing this mathematically using indicator functions. And the unobserved would be the flipped version of this, where you have ti, you have 1 minus ti, when you have 1 minus ti, you basically insert ti. Right? And then I spoke about this average treatment effect over expectation. And so there are some more technical details. I don't think I would have time to get into those. So I will skip that for the moment. You have something known as ignorability and so on, which basically, they make some assumptions when they build these frameworks. And so skipping through this, we have the expectation of y1 given x given treatment equal to 1, and similarly you have expectation of y0 given x given treatment equal to 0, right? Because this is actually what you see, because you have the observed outcome where you have treatment 0, and you have the observed outcome where treatment is 1 for some patients or some individuals. Right, so you can so what you would like to estimate is y0 given x given t equal to 1. This is what you would like to estimate, or you can estimate, or y1 given x given t equal to 0, and then you can take the difference between the two. Yeah, this is exactly what we're trying to do. Okay, skipping through this. So now, I mean, thinking of this intuitively, right? How would one go about doing this? So in the very simplest framework or very simplest thought process would be, hey, let's I have these patients, right? Some were given drug A, some were given drug B. What if in some of the dimensions or some of the features I can find neighbors? What are neighbors? So neighbors who were given the other treatment. So let's say I have this particular patient or I have a bunch of these red dots, right, who are given drug A. Can I find neighbors in this higher dimensional space which includes all their covariates? Can I find the blue neighbors, right? Then I can essentially what I can do is I can pick for every red data point here, I can pick all the closest blue neighbors and I can use their outcome values as a proxy for this patient who's the particular red dot and vice versa, right? Something like this. This is just one nearest neighbor. And this is what people started off with. So you started off with k nearest neighbors or one nearest neighbor, right? And then you have the individual treatment effect in this case. And this sort of works, it doesn't work very well. And the reason for that, very simply put, is that basically there are a lot of covariates or a lot of features which could bring two data points close to each other, but they may have no correlation or they may not be essentially causing the difference in the outcomes, if that makes sense. So what I mean is that you may have two people here, a particular red and blue dot, two data points who are close in age and years of education, and one of them might have gone into treatment and control, right? But then the difference in their outcomes may not be really caused by these covariates, right? It may not be caused by age or years of education. So that's something which you need to keep in mind. And similarly, you can add these as regression variables and build a linear regression model, but then that's always a concern that some of these variables, although they may bring data points close to each other, are not really causative in that nature. Remember, we're always trying to estimate something which causes this change. And again, I'll skip through this. So the nearest neighbor matching, again, basically, it's one nearest neighbor, but you can have k nearest neighbors, which is the simplest case. Interestingly, I'll show you something which I've worked on once I exit this PowerPoint, where we can bring in deep learning techniques to do something similar. This is a slightly different line of work. I'll come to that if I have time. Which basically generalizes this nearest neighbor approach. I'm using autoencoders and so on. I'll come to that. So and then you have basically instead of nearest neighbors, you have something. This is basically matching, and you can have different ways to do this, obviously. And there are a bunch of papers recently which have used different techniques to do this. Essentially, my interest in this was when I worked at Stanford as a research scientist. I worked with Professor Susan Ate and Hugo Imbens, and I actually helped build some analytical tools and packages in R and Python to do this, and worked on some of the modeling for this, where we were using random forests, and this is what I'll come to in a minute. And this is where I got interested in this about 5 years ago, and helped build some of these tools and packages for the analytics. And that's what I'll be talking about in a minute. I'll skip through this again since this is getting recorded. You can always go back and look at some of these references, or you can again feel free to contact me and I can share some of these with you. But then I'll speak about the general idea or the general intuition behind this. So let me start by talking about random forests first. For those of you who have worked in AI and ML, you might be familiar with random forests, or for those of you who have not, let me give a very quick introduction. So let me start off with a decision tree, right? So what do you do in a decision tree? Essentially, you can have a classification or a regression tree. And what a tree does is it looks at all your features and then it starts off with the top node and starts to split. It looks at every feature and then decides what's the best feature to split at, and then throws some data points into the left leaf and some data points into the right leaf. And it can be different cost functions you use for splitting. So in the case of classification, what you're trying to do is essentially you're trying to split based off of reducing the Gini impurity or basically the misclassification error. So you want all the data points which are in one class to go into one leaf and all in the other class to go into the other leaf and so on, right? And obviously you won't have that perfect split, so you keep on building a tree and you build, basically you build the tree and then you have some stopping criteria and so on. Now, what's a random forest? So let me start off with bagging first, right? So you have one tree. So what's the problem with one tree? You can have, typically the problem with one tree is that you can overfit because you can build a tree of depth 1000 or depth 10,000 where your every final leaf has just one data point, which would fit your training data set perfectly. But what's the issue with that? Once you bring in a test data set, it's going to fall apart, right? And the problem with that is that essentially the tree has very high variance, right? So you have a bias variance trade-off. It has low bias, but then high variance because essentially it's overfitting on the training data. So there are some ways to limit that for trees. However, you can do what's known as bagging, right, which is bootstrap aggregation, which is a concept from statistical modeling, or an older concept from statistical analysis or general statistics, where essentially you build multiple trees here, right? You look at random subsets of the data, which is similar to bootstrapping, and then basically you build multiple trees, and each tree looks at a random subset, and then you average the predictions from the trees, right? That's what is a bagged tree approach. However, there is still a problem which is a little bit subtle, and those of you who worked on this will probably understand that if you have certain features which are very strong, many of the trees will be similar to each other because they would be splitting on the same important feature at the top few nodes. So what you can do for that is randomized feature selection, and this is where the random part of a random forest comes in if you were not aware of it before. So at every node or at every splitting point, you randomly select a subset of your features or covariates, and then you split based off of that, and you keep repeating that. And this is a way to decorrelate different trees. So again, in a random forest, it's a forest because you have multiple trees, and all the trees are decorrelated. That's a that's a 2-minute introduction to random forests if you're not familiar with that. And typically, what is a random forest good for? It's been shown to be good when you have input features which are both categorical and continuous, and it can learn nonlinear functions. That's where the advantage of a random forest is. So if you look at the two diagrams here on my slide to the right, you can see I spoke about the k nearest neighbor, right, which is basically Euclidean. And by Euclidean, I mean basically it uses L2 norm, it looks at squared distances. And it can form neighborhoods like the circle which you see here, right? Or a sphere in higher dimensional space, an n-dimensional sphere or a hypersphere. Whereas with a tree-based neighborhood type approach, you can make hard partitions. You can have rectangles and squares, right? Typically rectangles, which would be the extreme figure on my right here, top right. Whereas on the left bottom, you see a random forest is more flexible because you're combining these multiple trees, which are hard rectangular partitions. But then when you combine a bunch of them, what you get is this essentially a soft weighting. So you have this irregular neighborhood, and then all the neighbors around the irregular neighborhood you can use for averaging. And remember, the whole reason why we came here first, right? Shouldn't lose track of that. So what we were trying to do was fix the missing data problem in causal inference. And then what I was saying is that you have certain data points which were the red dots, and then you were looking at the blue dots around them because some of them were treated, some of them were treated with something else. So you were trying to form this neighborhood. So a random forest actually is a very flexible way to form those neighborhoods. If you look at the figure on my bottom left here, it gives you this very flexible type neighborhood which is adaptive actually. It's adaptive to the data. But then the only problem here is that, or the only issue which we faced was random forest so far had been used for machine learning. And what does that mean? It was used for either classification or regression. Whereas in our case, we essentially want to build something which splits based on the treatment effects, right? Not on reducing misclassification or reducing mean squared error, which is a typical regression cost function. I think I'll skip through this, but this is important here. Whereas we're looking at the treatment effects here. So what we are trying to do is putting it very simply. At the top node, you start building each tree in the causal forest. So these type of random forests are actually called causal forests because they give you this whole notion of causality. You start off with the top node, and then you start splitting left, right, and so on as you would build a regular tree. But then you would split based on the treatment effect differences. So all the data points which go into the left leaf would have the treatment effect difference, which would be the difference in the outcomes here, which would be as different as possible as compared to when you look at all the different splits. You decide to split so that you maximize the difference in these outcomes between the left and right leaves. And you keep doing it, right, when you build an individual tree, similar to how we would have done with the classification tree. So it's a different cost function. And so the main contribution which we brought in when I was at Stanford is essentially this new cost function for a random forest. That's just putting it in one line. So the causal forest essentially is a type of random forest where we change the cost function, and so we are able to now estimate causal effects using that. That's just a simple two-liner of what we did. There are some more details again, and I think I'll, in the interest of time, let's see how much time I have left. Yeah, so in the interest of time, I think I'll skip it and just go and show you some examples here. And these are some results. These are again simulated results. Basically, you have the true effect here, which is the red versus yellow, and then you have the causal forest, and then the nearest neighbor, which doesn't learn these kind of hard boundaries very well, and then the causal forest can actually learn that pretty well. These are simulators, so again, it's not very interesting. So let me skip to something which is coming from healthcare. This is one example from healthcare. I have more, but then this is essentially for heart surgeries. And this will make it a little more concrete for those of you who got bored with all the theory. So we collected data from 35 hospitals. These are with some other collaborators. It's not just me. So we collected data from multiple hospitals, different heart surgeries. Now this makes it real, right? So the question we're asking is which hospital is better for which patient, right? And for which surgery. And there's nothing like one hospital is better for everything or another hospital is better for everything. That's exactly the type of subdivisions or the subgrouping we're interested in. We want to identify hospitals and surgery outcomes which are better for particular subsets of patients, and other hospitals and other outcomes, other surgeries which are good in terms of outcomes for other subgroups of patients. And patient features here are essentially the patient health related features, right? And then essentially we need to come up with a per patient metric. So how is this useful? Let's say a new patient comes to your, not an individual hospital, but comes to you and asks you essentially, I have this historical data for myself. I have risk factors, I have comorbidities, and what do I do next, right? And as somebody who needs to take a decision, you might tell them, go to this hospital X or hospital Y, get treatment X or treatment Y, and so on. And this is how it would be really used, because you don't want to really make the patient a guinea pig and try out a bunch of hospital surgeries. It's not possible. That's the whole idea behind actually building this framework. So we use the causal tree or the causal forest framework. We can treat a particular hospital as one treatment and another one as control if it's just two hospitals and so on. You can generalize this, of course. And what are the outcomes here? That's an interesting question. So the outcomes here are basically something which were collected from patients after the heart surgeries. They were given a big survey form. They had multiple questions. And then basically the patient filled out how they were feeling. And then you have the vitals from those patients. You have some recovery scores and so on, which came from the medical domain. So they have some ways to assess how the patient is recovering and so on. It is very interesting. Actually, it's not a trivial thing because you need to essentially pull up all this data from the questionnaires and so on, make it into, you can still have a vector, but you need to make it into a single vector or a single number, which is the outcome variable, right? And then what we do is essentially we use this outcome variable. You have all the patient inputs, which could be basically all the patient historic data, their age, their demographics, and all that stuff. And then that would be the X, and then you have the outcome Y. You have the treatment, which is hospital and surgery combination, right? Those are the treatments. And then basically you want to maximize the outcome difference. So you're building these causal trees, multiple trees, and then you're forming this causal forest. And essentially you come up with this. So on the left side, you have the regression tree approach, which is, and when I say it's regression tree, it's not the causal version, it's just the regular regression tree. I'm showing this so that you can compare figure 1 to figure 2. So in the causal approach, we build the causal tree, and then left side you have basic regression tree, which is looking at the outcomes and then using the hospital features and the patient features as inputs. So you can see here right on the very top, actually, you can see the difference here. So on the regular regression tree, it is actually picking up features which are important in terms of correlation with the outcome. So it's picking hypertension, yes versus no. It's called using that to split, right? Which basically is not very helpful for us because we do know that people who have high hypertension do probably have high risk for heart disease. Whereas here, if you look at the causal tree here, the top one it's splitting is actually a particular procedure. So it's actually picking this coronary artery bypass grafting, which is a procedure or an operation. And then it's using that to say what group of patients does it affect positively and negatively and so on in terms of outcomes, and basically it's causing other splits and so on. And another thing you will notice here is also the number of splits are smaller here in the causal tree versus the actual regression tree, which is more standard correlation version of that. And that's important because as you can see in the next table here, regression tree has a lot of splits, but if you look at the rightmost column, most of them are not very statistically significant here. Actually, almost none of them are statistically significant except one here. Whereas in a causal tree, you have fewer splits, but most of them are significant. And significant in what? That's the question. It's significant in actually predicting the difference between the outcomes for hospital 1 versus 2. So next time a new patient comes in, you can actually run the causal tree and tell them or predict, right? Essentially, in this case, you would estimate which hospital is better for that patient in terms of using all their input features to predict this. There are some other examples. I think I'll skip through that. I actually wanted to show some additional stuff which are not part of the slide. Let's see. Okay, so and so far what I spoke has been using random forest, right? Random forest for causal modeling, which is a modification of, like I said, a regular random forest, but then using the causal splits. So I'll also talk about a little bit about, remember I spoke about using nearest neighbors type approach. So can we generalize that? So again, I'll skip through this. I'm sorry, I don't have actual slides, so this I'll just go through the paper. You can find it on archive. Right, so one of the popular techniques which have existed for this kind of matching beyond nearest neighbors is what's known as propensity score matching. And for some of you who might have worked in biostatistics or general statistics, you might have come across this, right? It's very simple. So what it is actually a logistic regression model, right? I'll see if I have the equation here. So basically, you have a logistic regression model. You look at treated versus control, which is 1 and 0. So logic model essentially is a log linear model, right? You're trying to predict 1 versus 0 when you look at the log odds, and then your inputs are all the x's or the covariates. Now, the idea we came up with, or I came up with, is essentially can we generalize this logistic regression model, right? So this is a very heavily used workhorse in econometrics and statistics. So a lot of the matching, patient matching, etc., is done using propensity score matching. So basically, what you do is you fit this logistic regression, and then once you have that, for every patient for whom you have outcome for treatment 1 or 0, you look at neighbors, right? So it's a smooth version, and then you basically start looking at neighbors once you fit that logit model. Now, remember that the logit model can very easily be extended by adding more layers. If you look at it from a neural network perspective or a deep learning perspective, you can very easily add multiple layers and make it more generalizable. And you can, I mean, you can really go crazy with this, right? You can essentially add a bunch of layers, you can add dropout, you can do all the usual stuff which you do with deep learning. You can also add CNNs, RNNs, and so on if you have time varying covariates. That's something which I'm actually working on right now. And you can add that, and basically, the last layer would still be a logistic regression model. That is something which this paper presents, and I'll show you a couple of results so I run out of time. And other idea here is, let me actually show you the logistic regression stuff before I come back to this. Yeah, so we generated some simulated data, I have some real data as well, but I don't have it on me right now. So basically, this is the Swiss roll data set. So you can see that the k-means clustering obviously does very poorly on this, right? I mean, this is a no-brainer because k-means has no notion of manifold learning. It's just Euclidean distances. Whereas what we did was two approaches. So actually, let me talk about that. So the other approach is basically using autoencoders. And autoencoders essentially are a nonlinear way to reduce the dimensions and then still recreate the data set. So you have your x covariates, and then you are essentially trying to reproduce that x in terms of mean squared error. And essentially what you're trying to do is learn this manifold. Manifold is a low dimensional space which can be described mathematically in a higher dimensional space, right? So in this case, it's the Swiss roll. And you can see that basically k-means didn't do very well. Right, this is the figure which is showing this, and then you have manifold learning which does reasonably well, and then you have autoencoders which basically give the least error. And why is this useful? So this is a generalization in some sense of the nearest neighbors type approach which I spoke about for patient matching. And the one I spoke about just a minute ago was essentially extending the propensity score matching by using deep neural networks here. Right, and DNNs, which is basically you have multiple hidden layers and you have the output layer, and so I won't get into these details because you can find enough literature on this online, or many of you might have worked on this. So what I'm calling is for this is essentially what's known as a propensity net, which is an extension of the propensity score logistic regression model. And you can, of course, add any number of any types of layers and dropout and things like that. And basically, this is what we were able to build and actually show that this gives, excuse me, the mean squared error in terms of propensity net is actually much smaller than using just the propensity score matching, which is the logistic regression type approach. Right? And this is, again, this is not a very big data set, but I've used it elsewhere as well. So that's pretty much it for this. I have a couple of other things to show. Radhika, how many minutes do I have left?
So we have 10 minutes.
Okay. So I think maybe very quickly, I mean, there are some other papers. I don't think I'll be able to cover them in 10 minutes. So I think I'll probably pause here. There is some work in terms of time series analysis, which I did recently. And this is interesting. This is again causal modeling, but this is more along causal modeling for time series. And this is interesting at the present hour because this is related to some earlier work which I did, but also it relates to Covert interventions. And here, basically, what we looked at is essentially interventions in this case are lockdowns. Like multiple governments across the world had different types of social distancing and lockdown measures. And the idea was, can we estimate the difference in the activities before and after the lockdowns, right? So this becomes a standard, like I said, again, a standard causal inference problem because you want to know, I mean, you can see what the effect is of the lockdown, right? But you want to also estimate what would have been the activity if the lockdown had not happened, right? Which is again, like I said, this causal inference type problem. So it's a combination of two things very quickly. Change point estimation in the time series and then time series causal modeling. It's a slightly different type of model. But again, I invite you to look at the papers. Happy to send you these links later. But then the whole idea is, I'll show you in a minute. Yeah, so for example, this is the activity at the park. So you can essentially see there's a drop in activity. And basically, you can extrapolate from the previous time points what the activity was, and then you can see the difference in the outcomes here, which is what this is showing, right? So you can see basically the blue line and the dashed line is extrapolation of the activity before the intervention happened. So March 15 is when the lockdown happened in this case. And then the dashed line is the counterfactual, what I was talking about, which would be the estimated time series if the lockdown had not happened. So pretty high activity. And then beyond the lockdown, we actually recorded the activity levels. These are real data points, right? So the difference in these two using this model essentially gives you basically the difference in the activities or the difference in the outcomes, right? And this is a different flavor of what I spoke all this while, which would essentially be a time series version of what I was talking about. But yeah, in similar spirit, similar types of modeling approaches again. So anyway, I think I'll pause here now, and I can take any questions which people might have.
Dear participant, you can ask your doubts. Any question? Check your chat box.
So we have a question from the participant, and
Okay.
he's asking what can be an ideal source, or what can be the possible sources for getting data related to healthcare, the
Sure.
genuine ones.
Yeah. So possible sources would be your medical record data. I know in India, so I've worked with hospitals in India and elsewhere. So electronic medical records is not a big thing. Yeah, I mean, it's not centralized so much. So it's definitely an issue because each hospital has its own way of collecting data. But then I would actually ask you to go or basically recommend you to go to CBio portal. That's one data source, or TCGA, where they have a lot of data mainly in the oncology space. So a lot of cancer patient registry type data, where they have radiology images, they have pathology images, they have clinical outcomes, they have genomics data for a lot of different cancers. So again, it's TCGA, the letters T, C, G, and A. And if you just Google that, you will find a lot of data sets there. And people have analyzed that, so you'll find code and you'll find data sets there as well. So that's definitely one resource which I'm familiar with in terms of oncology, because a lot of my work has been in oncology. If you want to look at other types of healthcare data,
Okay,
again,
thank you
it's
so much, sir.
difficult to come by. So it would be it would depend on the use case and the domain you're looking at, right? So if it's not oncology, if you're looking at heart disease, for example, I'm sure you can find some public data sets, but again, it would be difficult to find big data in that sense. I think that's still something which people are trying to understand in the healthcare space.
Okay. Any other participant? If you can also unmute yourself or raise your hand, and we'll be able to unmute you and allow you to speak. Or you
Hello,
can
sir.
post the questions to us.
Hello,
Yes, please go ahead.
Madam. I am working for ECG, data transmission, real-time ECG. I have gone various hospital, but because of some privacy reason and hospital protocols, we didn't get that information or that data, ECG data for research work. So, is there is any alternate solution for getting this information or data for
Yeah,
analysis purposes?
yeah. Again, I would recommend. I mean, there are some sources online, right? Like AGNI and so on for brain imaging type data. So for ECG specifically, I'm not sure. I'm sure there are some public data sets, but again, off the top of my head, I can't remember any for ECG because I haven't worked on actual ECG type data. But again, public data sets, you should be able to find some. Again, they may not be like millions of data points, they may be like a few hundred to a few thousand data points. But that's a good place for you to start. Yeah, and that's the privacy issue is a big thing in healthcare, right? So that's one of the stumbling blocks. I think one of the issues with finding enough data and finding data which is useful, it's always an issue.
Okay, thank you, sir. Do we have any other participants? We have 2 minutes to go with, sir. Okay, I believe that's it. And thank you so much, sir. It is indeed an privilege to listen to such an eminent expert like you. Just going through your publications and your profile and the different roles that you have played over your uh, span of 15 to 20 years of your career, it is amazing and just beyond imagination how you will be able to, how you would be handling so many multiple things at the same time and still
Thanks.
be able to offer some time to us. And the institute is working rigorously in healthcare and agriculture
Okay.
using artificial intelligence. We also have a UG course in AI and data analytics,
Okay.
data science, and a PG course in artificial intelligence, and a lot of projects that we are doing under the same field. And
Okay.
someday when you come visiting India and you have a chance to come to Mumbai, so we'll be very happy that once the pandemic has settled down, we'll be able
Sure.
to show you the project. So someday when you have time, we can do it, arrange it online.
Sure, yeah.
And
We're
the
interested to
participants, I'm
learn
sure
more.
they would have got a new motivation.
Yeah, and just take one more minute of your time. So the startup I'm working for, Onward Assist. So basically, we look at radiology and pathology images like the slide I'm showing you. Basically, it's completely different from what I presented, but using AI and machine learning, basically computer vision and machine learning to do cell detection and cell counting in X-ray and CT scans as well as pathology images for cancer. So it's mainly using computer vision and machine learning algorithms for cell segmentation, cell detection, cell counting for radiology and pathology. That's what we work on. I just wanted to mention that.
Great, 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 sir. Okay, so this is how we could get your contact. So
Okay.
thank you so much, sir, and we are sure that under this initiative of STTP and with experts like you, we'll be able to train and motivate a lot of faculties and research scholars for contributing towards healthcare using artificial intelligence and data analytics. So I thank you on behalf of KJ Somaya Institute of Engineering and IT, and we hereby thank you for spending your time and re-invite you to please keep helping us. And thank you
Sure,
so much for
Radhika. Yeah,
accepting the
thanks.
invitation on a short
Thanks for
notice.
your
Thank
kind
you.
words. Hopefully, my presentation was helpful, and yeah, we can always continue the conversation
Yes,
on
sir,
this sometime.
definitely.
Yeah.
Yes,
Thank you
thank
so
you
much.
so much, sir. Thank you.
Thanks.
If you
So,
have 1
Vikas,
minute, a participant has raised his hand.
Sure.
Only if you have.
Yeah.
Otherwise,
hello,
you may
Vikas.
enter.
Hello,
Yeah.
Vikas. Sir. This is Mrudam Pandya. Actually, I want to know something about RAID assist. In your slide, you have just mentioned what is
Right.
that RAID? Yeah.
Yeah. So this is radiology. So we are looking at mammography. So we're looking at X-rays, and in the breast cancer screening space. So we're looking at X-ray images and trying to identify and localize cancer on the X-rays. This is detection of cancer lesions and scoring them. So risk scoring for patients on the X-rays.
The question I am asked because I am working on lung nodule classification
Okay.
in my research.
Okay.
So,
Yeah, we have
I
done some work on that as well on lung nodules, mainly in X-rays.
so can I get some guidance from your side if you are free?
Yeah, I mean, you feel free to contact me. I mean, not right now, obviously, but then you
Yeah,
can
of course.
contact me
Uh,
offline, and I'm happy to give some pointers.
yeah, sure. Thank you so much.
Thanks.
Okay, thank you
Okay.
so much, sir.
No
Thank you
other
for your
questions. Thanks a
time.
lot. Thanks, Radhika. Thanks, everyone, for listening. Bye bye.
Bye. Thank you so much. And I request all the participants to stay connected or join in next 20 minutes.